Hi. In this segment, we're going to discuss how to compute the stresses in a beam under pure bending. And the idea here is that we have a beam of a general cross-section, and we will look at a bending moment in around a given direction, for example, z. We're going to call it m sub z. And then in addition to that, we can have another bending moment about another second axis, which we would call m sub y. So the combination of these two should cause bending in different directions, and the interest here is to be able to compute the stress distribution in the beam. So I'll just start by outlining the fundamental idea behind simple beam theory that has no shear considerations for the moment, and then later we will look at the shear distribution in beams. So in this case, we will start by looking at the idea here is that we're going to start looking at coordinate system. And the coordinate system, as usual, we would have the x, y, z. So a beam is going to be aligned in this direction, and it has a neutral axis, as we'll see what the neutral axis is going through it. And in this direction, there's an axis that is y, and this axis here is x. And we're looking at a moment that is applied on the beam, and the moment will cause equilibrium, so it has to be in this direction, and this moment is going to be called m sub z. Note that the z-axis, this is the coordinate system. You have directions here, x and y, and the z is into the board. So the m sub z, the arrow that you see here, is going about the z-axis, rotating about the z-axis. So it's a positive moment, and the convention is that a positive moment acts on a positive face, because this is a positive face in the positive coordinate direction. So this is a positive face, and this is a positive moment because going into the positive coordinate direction. And if we just consider the stress distribution from that, the top part is going to be under tension, and then we expect that there's going to be a neutral point or a neutral axis, and the bottom part is going to be under tension. So we expect a stress distribution that goes tension and then compression in the bottom section, and that is the distribution sigma x that we would expect. The beam can have a cross section of any general shape. This is symmetric about the y-axis, so this is a y here, and taking the z-axis in this direction to be consistent with the with figure A. So this is B here. Then the centroid of the area is going to be labeled C, and the distance down, if we have an element, the element is right here. Let me make it a different color. So an element on this point here that has coordinates y and z is where we want to find the stress. So we're going to assume that the stress is linear, and linear meaning we have an axial stress that is proportional to y, and that all of the other stress components are equal to 0. So we have no shear, and also the normal stresses in the other two directions are equal to 0. And in order for us to develop an idea about the stress distribution, we must enforce first force equilibrium. And force equilibrium, it means that we must have the sum of the forces equal to 0, meaning the integral of sigma x dA is equal to 0. And substituting for the assumed stress distribution to be linear, so the integral of k y dA is equal to 0. And this is the condition that determines the centroid. So this is determines centroid of the area. So if we now move the coordinate system to the centroid, then we actually have force equilibrium already assumed. So we're going to move coordinate system to centroid. And we take the neutral axis to coincide with the centroid in that case. So having done that, then the second equilibrium equation is equilibrium moments, and the applied moment is mz, and that is equilibrated by the internal moment. So the sum of the moments is equal to 0, so mz is equal to minus the resisting moments, which is k times y, and then we multiply by another y, which is the arm length, to get the total moment. And therefore, from this equation, we can find that k is now equal to the m sub z negative divided by I sub z, where I sub z is the second moment of area. So every cross section has a second moment of area. For example, if we have cross section like a rectangle, and then we want to find the second moment of area about the z-axis here, and this is the y. Let's say the y is here, doesn't matter, in this direction here. So I have a z and a y. So we are bending about the z-axis, and the resisting part is this height or this length h. Then the second moment of inertia of area is b times h cubed over 12. So this is a property of the area. For every area, we find the second moment of area, and we use it in beam theory. For example, if we have a round cross section that has diameter d, then I sub z is the same as I sub y is the same as pi d to the power 4 over 64 for a round cross section. And obviously the maximum bending stress is going to be close to the top or the bottom, and the distance from the neutral axis to the top fiber, we're going to call it C. So this C is the distance from the neutral axis to top fiber in the beam. And if we divide by I divided by C, we're going to call it Z, and that's a section modulus. So simply put now, the maximum stress for design is sigma max due to bending is going to be m over z. So if we find the z, the section modulus, we should be able to determine the maximum stress. So these are kind of the elementary steps that we're taking to compute the bending stress in pure bending. So we don't have any axial forces, we don't have any shear. And what I'd like to do now is just go over a couple of examples with you to emphasize these points. One example is going to be straightforward, just one single moment, and then in the second example we'll have moments about the x-axis, about the y-axis, another moment about the z-axis. So let's go over these two. And what you see here is a T-section, and the T-section we have 1600 Newton meter. This is the moment that's applied. It's applied about the negative z-axis. So the z-axis is going this way. So the moment is applied negative z-axis means it is going to cause tension on the top fibers. So the tension is going to be here on the top, and compression is going to be on the bottom. So this is tension here, and this is compression. And we want to find the maximum tension and maximum compression in this beam. So in this case, first I need to find the location of the neutral axis, because that's where I'm going to locate my coordinate system. And in order for me to do that, I will assume that the neutral axis is a distance C1 from the top fiber and C2 from the bottom fiber. So this assumption, I need to find C1 and C2. Obviously the sum of these is equal to 100, so I just need one number. So for me to do that, I'm going to divide the T into two rectangles. The top rectangle is 1 by 12, and then the bottom rectangle is 12 by 88. And I find the area of this, and the total area is 1956. And then I want to find the moments of these rectangles about the top edge. So I assume that this area here is concentrated right at its centroid, and this area here is concentrated right at the centroid. And then if it is concentrated, it's like a concentrated mass, then or a force. Then I take the moment of that force or mass or area about this axis, which is this edge. And therefore I take the area would be, if I want to take the moments, the arm, the first arm of this area is 6 millimeters, because the total depth is 12, so half of it is 6. And then in addition to that, I have to have 12 plus half of 88, and that's 56, and locate the second concentrated mass. So the total area times C1 is equal to the moment of the first area times 6 plus the moment of the second area times 56, and solve for this give us C1 32.99, and C2 is now known. So once I know that, I need to find the total moment of area of the two rectangles. As I mentioned in the earlier part of the lecture, I is equal to BH cubed over 12, and H is the dimension about which you have the moment. So here is the depth. So for the top part, I have I cannot just add them directly. So what I'll have to do is I'm going to find the moment of area of the first one, the first area about its own centroid or neutral axis, and the second moment of area of the second area about its own axis that passes through the centroid, and then use the parallel axis theorem to transfer the second moment of area from area 1 to the common axis, and area 2 to the common axis. So let's go through these steps. I1 is 1 over 12 BH cubed. We find it. I2, again, 1 over 12 B is 12, H is 88 cubed, and that's obviously much larger than I1. And then what we do is we use the parallel axis theorem that I about an axis Z is I about its own axis, is the second moment of area about its own centroidal axis, plus the area times the distance square between the centroidal axis of the area to the common axis. So we have to find these numbers, D1 and D2. D1 is C1 minus 6. And D2 is again, C2 minus half of 88 over 2. And therefore, I found C1 and C2 and use the common, and then transfer the moments of areas to the common axis by adding the additional amount, which is area times d squared and area times d squared to find the total sum. Once I found the total sum, then I can determine the stress to be mc1 over I, and I now is the total, and that gives me 27.68, and the compressive minus mc over I, and that is C2 now, which is much larger, so you get a lot higher compression on the bottom surface. And that is a conclusion of that example. Now if we look at, we're going to look at another example. The other example is that we will look at the action of two bending moments about two axes. We know that we have an x-axis, a y-axis, and a z-axis. So x, and then y, and then z down. So we're going to apply a moment about the y-axis and a moment about the z-axis and find the result by summation of the stresses along the x direction as a result of these two components. So the formula that we use is just an extension, and that is sigma x equals minus mzy over iz plus myz over iy. And in case we have a circle cross section, we have two moments. The moments are vectors, so we can use a vector sum to find the magnitude of the total vector, which is square root of my squared plus mz squared. And it's a circular cross section, so we use the corresponding second moment of area, and c is d over 2, which is the radius. So this is a very special result, 328, the special result for shafts when we start designing shafts that have moments applied in two different directions. But in general, if you have a cross section that is like a T or an angle or a rectangular cross section, then we use equation 327. So let's apply it here. And in this example, I have a cantilever beam, and it's uniformly loaded in the y direction and the negative y direction, and then it has a concentrated force in the negative z direction. So the uniform loading is going to cause a moment, and the moment is going to be a negative mz, and then the moment about the y direction is going to be also negative my going in the y direction. And the cross section is 0.75 inch by 1.5 inches. So we first find mz about the origin, and that is it's a distributed load, so it's going down like this. So we add up all of this 50 pound-foot per inch multiplied by the total length of the beam and concentrate it in the center as if it's a concentrated load, and then take a moment about the z-axis, and that's a negative moment in here. So minus 1600. The moment about the y-axis, so let's work it together. We have y axis is going this way, and we have it here going about the y-axis 100 times the distance, which is the length of the beam, and the beam is 8 inches long. So we get my is equal to 100 times 8. It gives us 800 pound force inch. So the distribution of moments and forces, if you look on the XY plane, you get the force distribution downward, and the moment is resisting the force distribution at 1600. So it starts at 1600 negative, and then it goes to 0. This is a parabola. And the concentrated load gives you a moment of 800 and resisting the concentrated load. So 800 and goes down to 0. Now I have all the tools that allow me to calculate. The worst case is going to be at this point, because at the connection between the cantilever and the wall, I have 800 my and I have minus 1600 mz. So I need to figure out the stresses. So in order for me to find the stresses, I find I sub z, which is 1 over 12 bh cubed, and the h is in the, let's see, the h is in the y direction. So the h is in the y direction, and because it's I sub z. And then I sub y, 1 over 12 bh cubed. So h now is in the z direction for I sub y. So I found I sub z and found I sub y, and therefore I can use the formula minus m sub z times y over I sub z, and this is plus m sub y times z over I sub y, and I get the total value of the stress at point A, which is the top. And the compressive stress would occur at point B. So if you look at here, this is point B is the compression, point A is the tension, and these are the extreme on the diagonal where you have the extreme stress, because they are farthest points from the common centroid. So we will get a negative value for compression minus 11.38, exactly the same as the tension, because the beam is symmetric. If we happen to have a circle cross section of a diameter of 1 1/4, then the maximum value is 9.329, which is smaller than either one of these two. And I think that will be a good example that we can use in calculations for bending until we develop an idea about shear stresses in beams, which we'll do in the next segment.